we have taught about the Bode plot of gain, poles or zeros at origin, and simple poles and simple zeros. So I'm going to proceed this topic for quadratic poles or zero. So you are having the screen in which we have different plots of simple poles and simple zeros, system gain k, and if the poles and zero at origin. So in your last class, we have an idea about the corner frequency. Corner frequency is the frequency at which the slope is changing. So on your screen, when you are having a simple pole or simple zero, so you have a particular frequency which we are calling as corner frequency, and that corner frequency is dividing your frequency zone into two sections. One is your low frequency zone and other one is high frequency zone. So when you are having low frequency zone, you can see on your screen, in your low frequency zone, you are having magnitude in dB, and that is 0 dB. And for your high frequency zone, you are having magnitude in dB, that is minus 20 log omega t. And when you expand log omega t, you can also write log omega plus log t by the property of logarithm. So when you expand this one, this is minus 20 log omega minus 20 log t. So when you compare this equation with your straight line equation, that is y is equal to mx plus c. So your c is nothing but intercept at the y-axis, which is equal to minus 20 log t, whereas the rest one is having y is equal to mx. And when you compare this one, you will have a slope of minus 20. So it means for the high frequency range, when the frequency omega is very higher than 1 upon t, or omega square t square is very higher than 1, your that whole magnitude plot will follow this straight line equation whose slope is minus 20. So for this particular frequency, your region is divided into low frequency range and high frequency range. So what is the frequency at which these two range are going to divide? That is decided by a frequency called as corner frequency. And how you evaluate this? So when you compare these two magnitudes, just see on your screen. So when you have low frequency, you are having your slope 0 dB, and when you are having the high frequency range, then its frequency is minus 20 log omega t. So when you compare these two, omega t is equal to 1 or omega is equal to 1 by t. It means this is the frequency which is dividing these two sections. And this frequency is known as corner frequency. So this is a very important, or you can say by definition, what is corner frequency? Corner frequency is the frequency at which the change of slope from 0 dB to minus 20 dB per decade and represented by omega c. तो लास्ट टाइम पे ये थोड़ा सा डिस्कशन किया गया था एंड यू कैन सी द ग्राफ ऑफ दिस वन बोडे प्लॉट आपका सामने दिया हुआ है in which you can see omega c is equal to 1 by t. Till this frequency, the magnitude is showing that there is 0 dB. And after that, you can switches to the high frequency range. And as it switches to high frequency range, it will follow the straight line equation whose slope is minus 20 dB per decade. And you can easily verify that there is a corner at this frequency. That's why this is simply called as your corner frequency. Of course, if you are having an actual equation of magnitude plot, so you are having minus 20 log under root 1 plus omega square t square. What we have done till now? We have compared omega square t square with respect to 1, and according to that one we have decided a low frequency range and one high frequency range, but this is the equation which is having the actual magnitude. So when you put omega is equal to omega c, then you can see on the screen the actual magnitude is minus 3 dB. It means at this particular frequency from your graph, you can see that this is 0 dB, but in actual, this is not 0 dB. This is minus 3 dB. It means 0 dB से minus 3 dB down रहेगा. And that's why this plot is an approximate plot. We are considering 0 dB and minus 3 dB like on same point. But when it is asked that what is the actual magnitude at omega is equal to omega c or at corner frequency, this is not 0 dB. This is minus 3 dB. So ये अप्रोक्सीमेशन जो हो रहा है, क्योंकि ग्राफिकल मेथड में या अप्रोक्सीमेशन मेथड में हम कुछ assumptions मान के चल रहे हैं, जैसे कि we are considering this whole graph is divided into low and high frequency range. Why? Because if you want to discuss about the stability on a particular range, the system behavior is different. For other range, the system behavior is different. So our aim is basically we have to find out the reason at which your system will behave linear one, non-linear one, or you can say unpredictable things. So we have to consider the different frequency zones and on which we are discussing the behavior of the system. Similarly, if you take other frequencies, you will have magnitude that is like at omega is equal to 2 upon t, you will have actual magnitude minus 7 dB. So you can do all these things. So this is actually a concept of corner frequency and its effect on low frequency and high frequency range and its actual magnitude. So on your screen, you can see this is actual, your magnitude is changing. So when you are having omega is equal to 1, you are having omega c by 2, it is approximately minus 3 dB down, and you can verify this one at 1 by t. This is 3 dB down. At 2 omega c, it is nearly 1 dB down. So this is overall a variation or actual और what we can say जो approximation है इसमें variation होता है, right? Similarly, we can have a simple zeros. So the plot which is going downside, and downside का meaning मैं बता चुका हूँ that -20 or -40, this is showing the decrement in the slope. But when we have simple poles, that will be slope of 20 dB or 40 dB. It means this is showing a increasement in slope. So that overall projection in a positive direction. So you can see on your screen the same thing, but in this time the slope is going in the upward direction. Now similar way, if you are having simple and principal zero and its phase plot, so in the similar manner, when you have a pole, so its angle is minus tan inverse omega t. Why this is tan inverse omega t? Because mod g j omega h omega is equal to 1 upon 1 plus j omega t. So this is equal to, if you take the angle of numerator and denominator, the angle of 1 is 0 degree, and in the denominator that is tan inverse omega t upon 1, because in the time constant your real part is always 1, that I already discussed in your last class. In your time constant you are forming this equation in 1 plus form. So this is your overall angle is, in the numerator this is 0 degree, in the denominator that is tan inverse omega t. So when you put the angle conditions, that is 0 degree minus tan inverse omega t, because this is theta 1 upon theta 2. So this is equal to theta 1 minus theta 2. So that becomes minus tan inverse omega t. But if you're having simple zeros, so its angle is tan inverse omega t only, because आपको 1 plus j omega t is in numerator. So there is no minus sign. And it's, you can see the plot on your screen. Just put the different values of omega. You will get different angles, and just put that angles on your semi-log paper. You will have a graph which is nothing but a phase plot of a simple pole or simple zero. So phase plot is very simple as such as your simple XY plotting. Take the different value of omega, find out its angle, put that angle with respect to that frequency, and just interconnect that. As I earlier said that if you are having a constant, its angle is always 0. So there is no effect on phase plot if you are having a magnitude 1 or 10 or higher than that. So it is not depending on the frequency value, and that's why its angle is always 0. Now next is, we are moving towards quadratic factor. So again, when you are having a quadratic factor, first of all, you just resemble this one with your standard equation, and that is your s square plus 2 zeta omega n s plus omega n square. If you are considering quadratic poles, it means this term should be in your denominator. But when you consider is the quadratic zeros, you consider this term in the numerator. So in your screen, we are considering this the quadratic pole, so that we have taken this term in the denominator. First of all, again the same thing, just you have to form this equation to time constant form. It means 1 plus form. So ओमेगा एन स्क्वायर टर्म जो है वो से सबको डिवाइड कर दिया गया है, एंड यू कैन सी दैट दिस बिकम्स 1 अपॉन 1 प्लस 2 जीटा अपॉन ओमेगा एन एस प्लस एस स्क्वायर प्लस सॉरी एस स्क्वायर अपॉन ओमेगा एन स्क्वायर, राइट? Now next one is the same process. Put s is equal to j omega. When you put s is equal to j omega, you will have a complex denominator, and you know that when you open this one, j square is equal to -1. So you can put this denominator equation into real and imaginary part. So now you will have final one, 1 upon 1 minus omega upon omega n square plus j 2 zeta omega upon omega n. Again, now next is what we have to find out? Its magnitude plot. Again, the magnitude is x square plus y square का under root. It means real का square and imaginary square. So in the same manner, real part का square, it means under root 1 minus omega upon omega n का square का whole square plus 4 zeta square omega n square. Now next is its magnitude in dB. So in the similar manner, whatever magnitude you have, just put it 20 log and then magnitude. So you will have your final answer as minus 20 log under root 1 minus omega upon omega n का square का whole square plus 4 theta square omega upon omega n का square. This minus sign is because this term is in the denominator. If you are having simple in the sense of quadratic zeros, so this quadratic term in the numerator, so you will not have minus sign, and this is simply a difference between your quadratic poles as well as quadratic zeros. Again, do the same thing. Again, you divide low frequency range and high frequency range. So again, for your low frequency, just consider first term in the under root, that is 1 minus omega upon omega n ka square. So when your omega is very less than omega n, then omega upon omega n ka square is also very less than 1. So it means in comparison to 1, this whole term will be neglected, and that becomes only log 1, and log 1 is 0 dB. So that's why when you are considering again the low frequency, its magnitude is 0 dB. Similarly, when you consider the high frequency, your omega is very, very greater than omega n. But when you compare this one at the under root, your omega upon omega n to the power 2 is greater than 1. So you can neglect 1 with respect to omega upon omega n ka square. So when you neglect this one, this becomes omega upon omega n ka power 4. Now next is just compare this with the second term, that is 4 zeta square omega upon omega n ka whole square, and you will have that omega upon omega n ka power 4 is much higher than your 4 zeta square omega upon omega n square, as zeta is very low. So again, you can again neglect omega upon omega n square 4 zeta square with respect to omega upon omega n to the power 4. So at final, you have magnitude in dV, which is actually given in your screen, minus 20 log under root omega upon omega n का square का whole square. So one square quantity will cancel out with the under root. So you will have minus 20 omega upon omega n the square, or when you simplify this one, that is minus 40 log omega upon omega n, or in the simplified form, this is minus 40 log omega plus 40 log omega n. Again, you can compare this equation with the straight line equation, and this is y is equal to mx plus c. Again, we are not talking about the intercept of the y-axis. So when we draw the line, it will automatically intercept at the y-axis, which is equal to 40 log omega n. Whereas your m is minus 40 dB per decade. So when you compare this with a straight line, y is equal to mx plus c, you will have m is equal to minus 40 dB per decade. And as I earlier explained, as you are increasing the power of s, it will multiply by a factor of that power. It means when you have simple pole s, that is having magnitude slope is minus 20 only. When this is s square, this is minus 40. When it is having s cube, that is minus 60. So this is the power which is going to multiply with the 20 which is in front of that log omega, and according to that one the slope is changing. So because this is the quadratic one, it means we consider it as a s square term. So this is automatically multiplied to with 20, and it will give you minus 40. So be careful in that. When you are having any quadratic term, so its slope is minus 40 dB per decade, not minus 20. If it is simple poles or simple zeros, or poles or zeros at origin, its slope is always minus 20. But as you increase s square or 1 plus st whole square, so this is having two poles at origin or simple pole. But when you are having a quadratic factor, its initial slope is always minus 40. So be careful in that. Again, now the same thing. Now it's corner frequency. Initially, in a low frequency range, you are having 0 dB. And for your high frequency, you are having minus 40 log omega upon omega n. So when you solve this one for value of omega, you will have omega c is equal to omega n. It means your corner frequency is omega n. And you know what is omega n? Omega n is natural frequency. So natural frequency is the same way to calculate as I earlier explained in the time domain. What is that? When you have a quadratic factor, just compare this quadratic factor with your standard form. Just suppose you are having s square plus 4s plus 9. So just compare this equation with s square plus 2 zeta omega ns plus omega n square. So when you compare this one, you will get omega n square is equal to 9, omega n is equal to 3. The middle term just you compare with 4, already you have omega n term, you will find out the value of zeta. Similarly, तो ये ध्यान रखना है कि ओमेगा एन या जीटा बिल्कुल उसी तरीके से फाइंड आउट करना है जैसे हम लोगों ने पहले फाइंड आउट किया था इन योर टाइम डोमेन. एंड व्हेन यू हैव टू डू दैट थिंग इन योर Bode plot, just you convert this into your time constant form and divide this frequency into low frequency and high frequency range, and then find out its corner frequency with respect to your that simple method, and divide this plot into high frequency and low frequency. So on your screen in figure 12.17, you will have a plot of quadratic pole. You can see that when you are having omega upon omega n is equal to 1 or omega is equal to omega n, you are having a small dot, and till that we are considering this initial zone as a low frequency zone, and you can see that it is having 0 dB line. After that, we are considering the other zone as a high frequency zone, and we are considering high frequency zone which is corresponding with your straight line equation whose slope is minus 40 dB per decade. So you can see that on your screen. Initially it is 0 dB line. After that it is having minus 40 dB per decade line. And on that dot you can see that omega c is equal to omega n. And how you calculate the omega c? By using standard equation. In the same manner, what is the exact value at omega is equal to omega c? Because we have approximated this one with respect to 1. So when we are not having any approximation, its actual magnitude is minus 20 log under root 1 minus omega upon omega n का square का whole square plus 4 zeta square omega upon omega n square. So when you put omega is equal to omega n, then omega upon omega n is equal to 1, and when you simplify this one, you will have actual magnitude in dB is minus 20 log under root 4 zeta square, or after simplification you will have minus 20 log 2 zeta, and 4 zeta square is 2 zeta. And when you put different values of zeta, you will have accurate magnitude in dB. So when your zeta is equal to 1, you will have plus 13.97. Similarly, when you have zeta 0.7 value, it will have minus 2.92. And this minus and plus sign showing that this is up or downside. So if you are having zeta is equal to 0.1 is 13.97, it means this should be above to your 0 dB line. Similarly, when you are having zeta is equal to 0.9, its magnitude is showing, actual magnitude is showing minus 5.1. So it means minus showing that this is below the 0 dB line. So on your screen, you can see that when you are having quadratic pole with actual zeta value, and how you calculate the zeta value in the similar manner जैसे कि हम लोगों ने omega n find out किया था, compare with your standard form, you will get the value of omega n as well as zeta. So when you put that zeta value, you will have a actual magnitude at corner frequency. So put that magnitude and just you have to make a curve at that particular frequency. So when you have zeta is equal to 1, it means you can see that this is nothing but as a downside. When you are having zeta is equal to 0.1, you are having upside, it means that the 13 point something, 13.17. And when you are having zeta is equal to 0.7, this is in the downside. And why this is a curvish type of structure at that particular frequency? Because this will follow a parabolic structure. This is like y is equal to 4ax square. But when we have this corner frequency, your initial condition is coming in the low frequency range. So that is 0 dB. After that, this is high frequency range, this is minus 40 dB. But at corner frequency, actual is not 0. It is either up or down. So to reach that particular point, you have to make a curve. And after that, that curve will start from a point from 0 dB line, have a curve structure touch that point which is exactly at zeta value, and then reach to the second high frequency range which will touch the straight line of slope minus 40 dB per decade. The main thing is again at omega is equal to omega n, this should be actual magnitude. Rest, if you are having a slope which is slight, you can say more steep or less steep, it is approximate plot which we will consider it as a correct one. But at exact point, the magnitude should be whatever magnitude coming with the actual magnitude condition that should be verified. So this is the overall quadratic pole. In the similar manner, if you are having quadratic zeros, so you will have the same structure, but you can see initially the slope is 0 dB, and after high frequency the slope is plus 40 dB per decade. And the same manner you will have your correction at omega is equal to omega n, and when you put the different values of zeta, you will have again the magnitude at that particular frequency, and just plot it like this. So both the things are actually on your figure. So concentrate on the figure or plot, and after that just verify the exact magnitude at particular corner frequency and just draw it. Be careful that the high frequency, the slope is not minus 20, this is minus 40. Initially the slope is 0 dB. So it is a switching of 40 dB. So when there is a switching of 40 dB, you automatically understand that there is a quadratic term is introduced in this transfer function. अगर वो आपका कोई सिंपल पोल या सिंपल जीरो होगा, it means there is a switching of -20 or +20. But if there is a switching of 0 to 40 dB, it means there is a quadratic factor introduced in this one transfer function. In the similar manner, you will have a phase angle, and in the phase angle, you are having your g j omega h j omega. Take the angle of this one, and you can see on your screen the angle of one is 0, and the denominator, that is tan inverse y upon x, matlab imaginary part upon real part, and you will have minus tan inverse 2 zeta omega upon omega n upon 1 minus omega upon omega n ka whole square. Take the different values of omega and you will get angles, and just draw that angle in the similar manner as simple phase plot. And when you draw this one, you will have a phase plot, and you can just draw this phase plot in the simple manner as such phase plot जैसा भी आपको पहले बताया गया है. So this is overall a thing when you will have a quadratic factor. So in considering your transfer function, we have gain, simple poles and simple zeros, poles and zeros at origin, and quadratic poles and quadratic zeros. So when we have the idea of individual terms, we can combine these terms to concentrate on the different points, and we can construct the overall Bode plot. So these are your basic steps to sketch the Bode plot. First of all, whatever your GSHS is given, just convert it into time constant form. It means 1 plus form. Again, if you are having a constant term, draw a line of 20 log k. 20 log k is nothing but a decibel of constant term. Along with that, just see the poles and zeros location with respect to their corner frequencies. You have to, you can say, make a sequence according to the corner frequency. The first term is your constant. Second term is poles or zeros at origin. You always understand that either there is a pole or zeros at origin. Both the poles and zero cannot be in that question, because after that you have to simplify this one. And third one is, now you have to consider poles or zeros, simple poles or simple zeros, according to their corner frequencies. Whatever term you have, corner frequency less, just you have to consider that term first, and after that you will proceed on to the other terms. So this is overall today's lecture. We will take the numerical of this whole thing of Bode plot in the coming lecture, and we will also have the concept of stability by the new term called as gain margin or phase margin. So in the next turn, we will have the gain margin, phase margin concept along with problem based on a particular transfer function which will have all the terms including quadratic factor. Okay, so I'm coming on your screen. So anybody is having any problem till now on this topic, they can ask. Okay. It seems that there is no problem till now. So we are now finishing today's lecture, and in the next lecture we will discuss about the gain margin, phase margin, and numerical on this Bode plot. Thank you.